Hello, I'm Doug, and I'm going to describe 11 major problems in physics today. This was a talk I gave this very morning at the fall APS meeting at Wentworth Institute of Technology. Now, these problems break down into three areas: gravity, relativity, quantum mechanics, and kind of the bigger picture view of what's going on. So weak gravity is when gravity is literally 10 orders of magnitude smaller. And it doesn't work when it's that weak. That's like dropping an apple from a tree and having to wait 12 hours for it to hit the ground. These problems were first figured out in the 1930s when somebody said, hey, how fast does our galaxy move around? And he said, it looks like everything's going too fast. Then somebody said, look at those clusters of galaxies, and they're all moving too fast. And it took till the 1960s till somebody was smart enough to use something called elliptical integrals to figure out how to go from a disk galaxy and say, oh, there's a lot of light here, not so much there, and therefore it predicts there should be this type of velocity profile. And that work indicated there were two serious problems. The first is that it predicts the right peak velocity, but then says, there should be a decline in the velocity. And there wasn't. But the second problem is that if another galaxy comes by and gives it a little nudge on its axis, it's not stable. And so it should just curl up into a little ball. So we have two hypotheses on the table to deal with these. One is known as dark matter. And that is made up of stuff we haven't quite figured out, but we certainly are searching for it, that will be enough to get the right velocities. But it also has to be distributed correctly. In other words, it's got to be like spherically symmetric in order to make that disk galaxy stable. An alternative is known as MOND, or modification of Newtonian dynamics. And when you get in this weak gravity realm, the law switches from 1 over r squared to 1 over r. There are other areas of physics where that does happen to happen. It just is not so elegant. But even more importantly, there is some new data about like a bullet galaxy passing through another galaxy, and when you have that situation, you can say, hey, is the mass separate from the potential? And it is. And that's really tough for MOND to explain. There's a problem with old gravity. By that I mean the stuff of the Big Bang, when the universe started. Because if you look at the math, you say, well, either the galaxy should just not get out of bed. It should just say, forget it, I'm not starting up. Or it should just fly apart so fast that nobody has time to form a galaxy. Our stars, or us. This place where we are, where there's, everything's kind of flat, gravity is not too strong, that shouldn't happen. It's like balancing a pencil on the lead, on its lead. It just is, it doesn't want to be there. All right. There was also a problem that everybody's traveling at the same speed, to 1 part in 10 to the 5. And the problem with that is that the universe has got areas that are space-like separated. They can't talk to each other to agree on that velocity. Like, there's no way they could. So how do we deal with that? Well, one hypothesis on the table is known as inflation. That there was this inflataton that was there very, very, very early and said, hey, just go like crazy, people. And that way we can solve both of these problems. And it does, as long as there's an inflataton. We have a problem with big gravity. So gravity attracts. So you say, I bet stuff is slowing down. Thoroughly reasonable. And so people said, it's so reasonable. We are going to do the work to figure that out. and they collected this data from type 1 supernova, and the answer was not that. Apparently things are accelerating. And how do you deal with that? Well, you give those guys Nobel Prizes, and you say, well, maybe there's dark energy, which is kind of like the cosmological constant coming back to life. Maybe that does it. We also have a problem with small gravity. By that, I'm talking about having gravity work nicely with quantum mechanics. What does it mean to play with quantum mechanics? Well, you start with your field equations, and you invert them, but because it's got this gauge symmetry, you've got to pick a gauge, and you end up with a propagator. Then you use a propagator and perturbation theory, and if you're really incredibly good, you can do some calculations. I think I did those once, many, many years ago, but I probably couldn't do them today. All right, so that kind of program works for EM. Okay, in fact, that's what I showed right there. But not so much for the 10 nonlinear equations of quantum mechanics. And it's been clear since the 20s that, we've got to get these two together, and nothing has really worked out so well. Now, folks who work with strings, they say, hey, I think we're going to do it real soon. And please keep giving us those $3 million prizes. And then there's also a smaller group that works with loop quantum gravity, which are solutions to the Einstein field equations that look a little bit like stuff that shows up in quantum mechanics, and so therefore there's a hope that they can build a bridge. Now they're still working on their bridge, but we can wish them luck. Personally, this feels more to me like the 1800s, when there was this guy who was just amazing at predicting where planets were. He was a celestial mechanic guru. He was so good that he said, I can't explain this, some of the motion going on here. I think there should be another planet like right over there. And he predicted where Neptune should be. I mean, he was that good. And this is all before computers, okay? So he said, there's a problem with the precession of the perihelion of Mercury. I know the Sun and Mercury, what they should do together, and I've accounted for what Jupiter does, and Saturn, and Neptune, and Venus, and the Earth, and we're missing 43 arc seconds per century. It's not a big problem, but he said it's real. So he said, I predict, like I did with Neptune, that there's a planet behind the Sun, the planet Vulcan. Now this is pre-Star Trek. This is pre-electricity in homes. But time and money was invested to find the planet Vulcan, and it didn't work out. So there was this one observational thing, and there was one theoretical problem with Newton's law, and that was that it wasn't consistent with Einstein's special relativity. And that was probably the biggest driver, but it was those two reasons why Einstein eventually came to general relativity. So he replaced the entire intellectual structure for describing gravity. I personally feel we're in that same situation, only we've got three things we're looking for and one theoretical problem. So the three things we're looking for is dark matter. We're spending good money looking for it. Dark energy. We're spending money looking for that. And the inflataton, maybe we're not looking for it, but that's a third thing. And then we've got a theoretical problem that we can't get our field equations to work within the structure of quantum mechanics. And to me, that's solid enough reason to say we should look for something like totally new, people, which is something I do. It's next to impossible to succeed because there are so many tests you have to pass through. But in my limited free time, I do dream along those lines. All right. So let's talk about a different problem, small physics. Why is quantum mechanics weird? And this is a drawing of the two-slit experiment. These debates have been going on since, you know, the 20s with Einstein and Bohr. And you get your choice now. Copenhagen, which is kind of passé. It's just too old school. Many Worlds is pretty popular. Balm is pretty cool. Pilot waves, that kind of stuff. But there's actually no real winner. But this actually doesn't feel like physics. I mean, real physics is they'll go, this is the answer, and there is no debate. If you disagree with the answer, then you are wrong. Now, I think we should get to that same state with what quantum mechanics means. And we're not there. But I think that's a problem worth working on. Then there's fast physics. So I completely agree that something with mass cannot go faster than the speed of light. And I should say, a couple of years ago when there was a report that said, well, maybe we've got some experimental data that says you can go faster, I said, I'm not buying it yet. Please go back and check absolutely everything. You know, how your fiber optic cable connects to computer boards in Italy, which it turned out to be the problem. Okay, no, I didn't predict that. Okay, but that really was the problem, was the soldering issue or something. Now, so this great solid data to say it's wonderful, spot on, and the theory is absolutely gorgeous. Special relativity just rocks. It's just beautiful. And people are actually kind of pleased with it. They say it's just a property of the Lorentz group. Look, I want something I could explain to the person on the street as to how nature imposes that speed limit. Okay? That's like obviously so rock solid you go, yeah, duh, you can't do that. All right. So now how about combining those two, small and fast physics? Well, I'm talking about calculations that are done in relativistic quantum field theory, because you have to like manage infinities using something called regularization and renormalization. So you start with the field equations, you invert them by choosing this gauge, and you start to do perturbation theory, and this was all developed in the 40s, and it makes the most precise calculations in all of science. And so that's why a lot of people are completely at peace with this issue. They say, yeah, the old masters might have complained, but I'm kind of still with the old masters. I'm still with Feynman and Dirac, who were just uncomfortable. They just said, golly, I wish there was something better. And I'm still in the golly, I wish kind of phase. But it's a tough thing, a tough problem to do anything on. But I think something should be done. But what about the fundamental forces in nature? There are four of them. There's gravity, there's EM, there's the weak force, there's the strong force. Long history of finding these things and trying to characterize them, and we've got it down to some groups. Now, I've only heard a fellow named John Baez talk about this DIFM group. I wish kind of more people would kind of go into it. For EM, it's simply this group U1, which is unit complex numbers, and SU2 is unit quaternion numbers, and the strong force is kind of SU3. So you say, well, if you want to unify them, why don't you go a little bigger? And people have worked on SU5 and SU10, and those kinds of things suggest there should be a lot more particles that haven't been seen. So, that's a little tough. Now, people who work with strings, they say, hey, yeah, get on our bus. We explained everything, including this kind of situation. I don't know. So that brings us to unified physics. Come on, put everything together, make it a beautiful picture. Why does nature work from the small, the tiny, the Dirac equation, up to the huge general relativity field equations? And the history of this is that when physicists retire, that's what they work on. It's like, come on, everything should be coming from one kind of place. So let me give you a flavor of where I'm researching. I haven't worked it out, okay? I own quaternions.com. So, of course, I've got this quaternion bent on me. But the quaternions are defined over the 4 real number lines. And when I draw those out, I'm really bothered by them. Because, see those 4 zeros? It's like they have, in a topological sense, nothing to do with each other. And that's like, that's not repairable. You can't, I'm going to just tie a rope around them and say, be close. No, topology is about connection. And the only way I could get around that is to draw this little star pattern, which is all well and good until you start thinking about it. And then you go, hold it, there are no minus signs. And I'm like, but every math, physics, programming tool I've ever had assumes the real number line's there, okay? What does it mean I go to 0 and don't know where to go next? You know, it's like if I'm, how do you work with this topology? I don't know. But that is where I'm working, and we'll see if it works out at all. And this one's more concrete, the arrow of time problem. And that is that the laws of physics seem to not care. But the universe, it's like, obviously cares. I mean, it's, so our equations like Newton's law, you put in a minus t, doesn't matter, we got 2 of them. Use the member of the Lorentz group to flip signs, and it's like, yeah, it doesn't matter. And then there's this CPT theorem that deals with groups, and it says, yeah, it's all the same. And this goes back actually to Boltzmann, who, when he was thinking about the second law of thermodynamics, said, you know, as long as there's a little asymmetry, I can just build everything out. It's just I don't have any way to put in that little asymmetry in time. So it's a deep problem. So people do use information theory and this holographic principle. People are trying to apply that. But still, this is not one where people say, oh, that's the right answer, and if you don't have the right answer, you're wrong. And finally, the 11th problem, as it were, I call visualizing physics. And that is because people can't understand the algebra that physicists use. You know, those boards on the Big Bang Theory. Nobody gets them, except the PhD guy who writes it. But people do get pictures. I mean, you could go up to people on the street and say, what is the minimum of y equals x squared plus 3? And like, no one would know. They just, oh, not no one, but if you're in Cambridge near the MIT campus, maybe a lot of people would know. But in the general street, nobody's going to know. If you show those same people the graph, okay, and say, where is the minimum, they're all going to know. In fact, they're going to be insulted. It's like, I know that. What could be more obvious, okay? So imagine this future where we have analytic animations that are faithful to the math of, say, the hydrogen atom. And so we say, hey, look at this excited hydrogen atom. And look, it has to emit a photon of this frequency, and now it's less excited. I think if you had that full 30-second animation, everybody would go, duh. Well, we're not there now. I could look up the equations for the hydrogen atom, and I probably couldn't do a darn thing with them. It's hard algebra, and therefore it's going to be hard animation to create. But at least I think it's certainly something worth working towards, and it's one of the 11 problems that I do spend a little bit of my little free time thinking about. Okay, thank you very much, and I hope you like this characterization of some deep problems in physics. Thank you.